Good morning, good afternoon, good evening, depending on wherever you are watching this from. Welcome to Weekly Science Review from Gayathri Labs. In this session, we take an open access article and then go through the discussion of the paper. And then after that, we have Q&A. Typically, professionals from world over participate and present. And today, we are glad to have a presentation from Gayathri Sridhar, soon to be Dr. Gayathri Sridhar. She's a PhD student at IIT Bombay and Monash Research Academy. And the topic is right in the screen. So looking forward to learning a lot more about NDE and the magnesium dissolution. Over to you, Gayathri.
Yeah, thank you, Chalk, for the nice introduction. So good evening and good morning, depending on wherever you're calling from. I'm happy to present this week's weekly science review for Gayathri Labs. I'm Gayathri Sridhar from IIT Bombay and Monash University. So the topic that I will be discussing today is the pH dependence of magnesium dissolution and hydrogen evolution during anodic polarization. So this is an open access article in the Journal of Electrochemical Society. So before we jump into a lot of discussion, I want to briefly say why I have selected this topic. So hydrogen evolution is a simple yet complex reaction, as we all know, and it's everywhere in electrochemistry. So earlier, it used to be deemed as a parasitic or detrimental reaction, and it drives, for reasons, because it drives metal dissolution during corrosion, it's a parasitic reaction in batteries, and it reduces current efficiency during electroplating. Over the past few decades, this hydrogen has become really famous as a potential and sustainable energy future for the world. So more than ever now, it becomes really important for us to understand which factors govern hydrogen evolution on a given metal surface, and which is why I have chosen this topic. While energy people are more focused on looking at potential substitutes for precious metals such as platinum, it's also important to understand other metals like any metal surface for that matter that's capable of evolving hydrogen and how to tailor hydrogen evolution on them. So, which is why I've selected this topic. So moving ahead, since this weekly science review is focused on the gathering of this weekly science review is mostly for energy people. So I wanted to give some basics on corrosion before we jump into the paper so that it will be useful for you to follow. So corrosion in general is metal dissolution, and it happens because metal tends to go back to its thermodynamically stable oxide state. When I say this is oxide, it is just a terminology, but in general, metal just transforms itself into its most stable state, which is the ore from which it was originally extracted. So in this process, as the metal undergoes dissolution and the electrons that are generated gets consumed by another reaction. So shown below here is a simple electrochemical reaction involved in metal dissolution. We have metal dissolving as Mn plus and N electron minus. And since we are discussing hydrogen evolution in this paper, I have written 2H plus 2 electron gives hydrogen. But depending on whatever system we are looking at, this can be different. It could be oxygen reduction reaction, or it could be another reduction of another metal. It just depends. So let's stick to hydrogen evolution here. So these are the reactions that we would see under open circuit potential or the freely corroding condition. So as a corrosion engineer, we are more inclined towards understanding how the material would perform at a different potential or a current. So for this reason, we run the so-called tafel polarization or potential dynamic polarization. So the curve that you get from a potentiostat is ideally this green curve, wherein we have two arms. One arm is the reduction arm, and the other is the oxidation. So both of them intersect at a point when we do a fitting, and we mark that as the corrosion current and as the corrosion potential. So now this is the picture that we get from a potentiostat, but what ideally happens thermodynamically and kinetically can be explained based on mixed potential theory. Before you get overwhelmed by this little figure here, let me tell you it's very easy, just allow me to explain. So let's say you take iron and then you drop it in water. we have two redoxes. One is ion reducing and then ion oxidizing. So similarly, in hydrogen, you have hydrogen evolution and hydrogen oxidation. So the point that you see here is nothing but the reversible potential for this reaction to happen and the exchange current density for this reaction to happen. So if we draw these curves based on the slopes, then we end up in an intersection point, which is the corrosion current density and the corrosion potential that we see in a potential stack. So this is a mixed potential theory. So we also have to note one thing as we move forward, which is during anodic polarization, the electrons that are getting generated during metal dissolution are conveyed to the counter electrode via the potential stack. So this is something simple. As we handle the potential stack, we would know that the electrons are not generally consumed on the surface of the metal itself, but it is consumed at the counter electrode. Now, with this brief introduction, let me introduce you to the concept of negative difference effect. So before I can also explain this further, let me give you a heads up that we're looking at magnesium, which is capable of forming a very unstable oxide film on its surface. So when I say it forms an oxide film, it's passive, meaning it's not going to dissolve at a rate that any active metal would dissolve. So for instance, if we drop iron in an acid, iron is going to dissolve and form iron 2+ and 2 electrons. Whereas when we drop a passive metal which has a passive film on its surface, such as aluminium, it's not the aluminium that's dissolving, but yes, of course, it's aluminium that's dissolving, but the surface immediately in contact with the electrolyte is nothing but aluminium oxide or the passive film. So with that in mind, let's proceed ahead and see what's negative difference effect. So if we take this potential as the corrosion potential, anodic polarization is basically moving forward like this. And what we see is as we move forward, the hydrogen evolution reaction should actually decrease. So this is what we would expect according to a standard Deiffel rate equation designed from and based on Butler-Wehrmeier equation and everything. But in metals such as aluminium and magnesium, this actually hydrogen evolution increases as the anodic polarization also increases. So if we were to plot hydrogen evolution current density versus anodic current density, a conventional Deiffel rate equation would mean that it decreases. But during NDE or the negative difference effect, this hydrogen evolution current density increases along with the anodic current density. So why does this NDE really happen? So it depends on the alloy system that we are interested in. For instance, I worked in aluminium, and aluminium has an entirely different model for why NDE occurs on this. So for the NDE in magnesium, it is because of two important factors. One is magnesium is a very active metal. If we look at it, the EMF series, magnesium is much active than many other metals. So if we were to consider a pure magnesium, it's going to have impurities such as iron or any other metal embedded in its its surface. So since magnesium undergoes high dissolution, these noble elements tend to enrich on the surface and they start acting as cathodic sites. And once they start acting as cathodic sites, they are basically going to support hydrogen evolution. And this is one reason that people think is the reason for the NDE. Another important factor that people consider is the protective passive film that's present on magnesium, which is very weak. It's partially protective or very unstable. And when this passive film kinds of disintegrates, then you have a highly active surface that gets exposed to the environment. And so the NDE occurs. So now these are the basic reactions that occur during magnesium corrosion, which is the magnesium dissolution, which is anodic, and then we have a hydrogen evolution, which is cathodic. And then the Mg2+ reacts with OH- and forms a film, which is magnesium hydroxide. So now there is a competition between the film formation and other reaction, which is hydrolysis of Mg2+. So depending on which reaction occurs, the structure of the protective film is going to change, and it's going to alter the corrosion or dissolution phenomenon of magnesium. So since this reaction, the competition or the kinetics is dependent on the pH, people are interested in understanding how does a pH really affect the dissolution of magnesium, which forms the objective of this paper. So while many people have done this in prior works, this study is kind of unique because it uses a so-called electrochemical flow cell. So what is this? So this is one new technique that has been introduced to the field of corrosion science called atomic emission spectroelectrochemistry. So what this does is that we have a working electrode which is connected to the potentiostat depending on the reaction that you would like to perform. We have electrolyte which flows inside the electrochemical cell, and then it pops out, and then it's delivered to a mass spectrometer, where the chemistry of the electrolyte that comes out is kind of investigated, and then depending on the process data, we can calculate the dissolution current of the Mg2 plus based on Faraday's law. So this is called a scanning electrochemical flow cell in this study. So this is kind of a very sophisticated technique where we get real-time information of what's happening. So if we were to record the potential variation or the current variation at the electrode surface, we would also get a simultaneous dissolution current, which we can study and then correlate it back to all the electrochemical signals that we see. So this is one of the unique features of this study, where they try to analyze the magnesium dissolution and hydrogen evolution using the electrochemical flow cell. And they use buffered and unbuffered electrolytes to study the effect of pH. So in the case of unbuffered, you are basically allowing the metal to corrode at its own natural pace, whereas when it is buffered, you try to tune the pH at the surface of the magnesium, and therefore you have a very controlled experiment to see how the surface actually responds. So the methods used for this study were they chose magnesium which had about 17 ppm of iron, and they used unbuffered 0.01 molar NaCl and some buffered solutions. So their idea was to see dissolution current, which is this one. And then they also wanted to see a semi-quantitative kind of hydrogen evolution rates. So for this, they tweaked this ICP-MS a little bit to sense the gases that are evolving. And then with this, they also wanted to compare this data with hydrogen collection setup, the hydrogen collected using a hydrogen collection setup. So this is the metal that is magnesium in our case. We have an inverted funnel, and over it goes the burette. So as the metal corrodes, we have hydrogen gas that evolves, and that gets collected in the burette. So depending on the volume that's occupied after a certain period of time, we know what's the volume of hydrogen that's generated. So with this setup, they try to study the magnesium dissolution in 0.01 molar NaCl. So let's say they started at OCP somewhere here. So this is basically galvanostatic anodic polarization, which means they are applying a current, which is the dotted lines, and then they are measuring the dissolution current, which is the black lines, the solid lines here, which is from the from the mass spectrometer, and they're also simultaneously measuring the potential or recording the potential. So the red lines here, so let me tell you that all the line color that I have shown here represent one phenomenon. So if you're discussing at one point, meaning we have to compare all the red arrows. So they tried to see the dissolution current at 3 different points. What they saw was that the dissolution current during the OCP at the first stage was similar to the dissolution that they observed after one set of anodic polarization. And then they were again able to see the same kind of dissolution current after a second set of anodic polarization. Well, the steps are all similar, but we see that polarization is here, the dissolution is much higher. However, after the end of the polarization, they were able to see that the dissolution current comes back, falls back to the same value. So what's interesting here is that though the dissolution current falls back to the same value, they found an ennoblement in the OCP after every polarization. It's kind of interesting because earlier they always said that this ennoblement was due to the enrichment of cathodic particles, which kind of increased the magnesium dissolution. But what we see in this data is that the magnesium dissolution current is not really changing. However, there's a change only in the potential, which means it strongly indicates that the surface is modified and has a different chemistry. So the second thing that they observed was the blue arrows, which is the fluctuations in the applied current. So when they were measuring the dissolution current for magnesium, they could not measure the hydrogen evolution. So it was either the magnesium dissolution or the hydrogen evolution. So in this case, they just measured the magnesium dissolution. But what can be seen from this data is the fluctuations, which actually represent hydrogen evolution. So initially the fluctuations were not that great, but then they increased during the second polarization, which again states that after this polarization, basically the surface changed different. I mean, it was very different from what they had during the first polarization. And they also found that the dissolution current during the slope, the negative slope of this particular curve, was very high as compared to the dissolution current that they saw here. So as I will summarize in my conclusion slide, what they tend to say here is that this whole phenomenon they attribute to two different factors, which is the instability of the passive film plus the enrichment of the metal impurities at the surface. So, so now that the study they have done studying the dissolution current of magnesium, the next study they wanted to do with hydrogen. So before we go on to that, let's see what is the mechanism that they are proposing based on this data. So at OCP, magnesium dissolution generates alkaline pH. So they have a magnesium hydroxide film. And then when there is a very low anodic polarization, say the first few steps of this anodic polarization when they do, they have magnesium dissolution, and then they have the slight amount of enrichment happening at the interface. So when it is high anodic polarization, that is, they try to increase the current to a much higher level. They have a completely different oxide film here, which is completely enriched with noble metals, and that kind of increases the hydrogen evolution kinetics. So when they bring it back to OCP, well, these films still remain, but then due to the potential, they again have a magnesium hydroxide film, but this film is much porous and different as compared to the dark film. And because of these changes in the surface film characteristics as a function of pH, they state that the ND occurs in magnesium. So I think this is again just the magnesium dissolution current and not the hydrogen evolution. So they took two different solutions, one with a buffer, borate buffer of pH 10.5 and the other with a citrate buffer of pH 7. And they tried to increase the steps after an OCP. So what they found when they compared pH 10.5 versus pH 7 is that the OCP current was kind of much higher in the case of pH 7, that is with relatively lower pH, there was more dissolution. And then the fluctuations in the current, which is they attribute to hydrogen evolution, was significantly higher when it was near neutral pH. And what they also saw is that the difference between the applied current, which is the dotted line, and the solid line is much smaller in the case of pH 10.5, whereas it was much higher in the case of citrate buffer of pH 7. So with this, they kind of concluded that in the case of higher pH, the film that forms is very stable, and it kind of supports it curbs metal dissolution, whereas in the case of citrate buffer, okay, I'm sorry. Yeah, so in the case of citrate buffer, they have higher dissolution and a completely different oxide film, or sorry, passive film, which does not support, which enhances the magnesium dissolution. So before I proceed ahead, let me just ask you, is my screen visible properly?
Yes.
Chalk?
Yeah. Yes. It is visible.
Okay, fine.
Yeah, we
Thank
can
you.
see the laser pointer very well. No, no issues.
Okay, so my screen turned out to be a little bit dull. I am not sure, so you will able to see it properly. Fine. Okay, I'm continuing with the presentation. So now that they have studied the Mg2 plus dissolution, now they wanted to study the hydrogen evolution. So for this, what they do is they change the mass spectrometer a little bit, and they used a different gas permeable membrane to sense the hydrogen. So now in these experiments, they were not measuring the Mg2 plus, rather they were measuring the hydrogen evolution. So this is semi-quantitative, meaning they're not able to study the exact amount of hydrogen evolving and its quantitative measure. But yeah, so they try to compare the unbuffered solution, which is this, with the buffered solution, which is this plot. So what they found is that in unbuffered solution, the pH at the metal surface was changing drastically, and so they were able to see that the fluctuation was really high, and the hydrogen evolution current constantly increased. Whereas in the case of buffered solution, what they found was quite interesting, because when they tried to increase the applied current, they found that the hydrogen evolution actually decreased in buffered electrolytes. All the fluctuations that they show here, that they attributed to the formation of small bubbles from the surface, the release and the attached bubbles give sort of fluctuations in the measurements. But what they were able to see is every time they tried to rise it to 5 milliamperes per centimeter square, they were able to see that the hydrogen evolution basically dropped. And then it only increased when the dissolution current was more than, say, 15 milliampere per centimeter square. So with this, they concluded that the protectiveness of the surface film is entirely dependent on the surface pH conditions, and that alters the hydrogen evolution kinetics. So in the unbuffered solution, they wanted to see what happens, how does the pH really changed in an unbuffered condition. So for this reason, they took a split cell and then they added 2 beakers, and then this a whole lot of setup. They had magnesium on both the sides, and then they tried to study the cathodic pH and the anodic pH and found them to be highly alkaline. And what this means is that the relatively lower pH in the anodic side, which is not very high in my view, it's just 1 point, but they attribute it to the hydrolysis of metal ions in the solution. So what they say is that the hydrogen evolution that occurs due to NDE causes the surface pH to become relatively high in the case of unbuffered solutions. So now that they had done all the flow cell and everything, which has electrolyte convection, they wanted to try out collecting hydrogen in the case of in an undisturbed setup. So for this, they had so they took different buffered solutions. The one that you find here is the unbuffered solution. So at OCP, what they found is that the pH3 was always having a higher hydrogen evolution rate as compared to the other other buffered solutions. So they attributed to the differences in the surface chemistry, because in alkaline pH, the film that forms upon magnesium is soluble, whereas at pH3 and pH7, no NDE was observed. However, when large anodic current densities were applied, they were able to see that the surface pH in the vicinity of magnesium tend to be almost similar. So for this reason, they stated that the hydrogen evolution almost was same in pH7 unbuffered and pH 10.5. So after all these experiments, they were also able to visibly see that the magnesium surface was distinct. meaning the oxide or the passive film, whatever formed, had differences in the color. Some were black in color and some were lustrous. So they were able to clearly attribute the differences to the differences in the passive film. So the conclusion of their paper is that the hydrogen evolution upon magnesium during anodic polarization is influenced by a combination of factors, which is not just pH, not just applied current, not just the duration of anodic polarization, but a combination of all. So it could be it could be pH plus applied current. It's not always just the applied current. So how do these factors really impact? They affect the stability of the surface film, and they also lead to excessive dissolution, and that causes enrichment of noble elements, which in turn support the hydrogen evolution. So the takeaway from this presentation, in my view, is that the corrosion resistance of magnesium or the reduction of the hydrogen evolution upon magnesium can be improved by changing the surface film characteristics. And many metals such as magnesium exhibit NDE and can generate hydrogen when in contact with saline water. So with that, I open the forum for questions and discussion.
Great. Thank you very much, Gayathri. That was very well done. And you really took the time to do the introduction of the subject very well for all of us who have not been working in corrosion for a while. So that was very well done. Thank you for that. Let's open it up for questions and discussions from the team.
So should I stop sharing, Chalk?
Yeah, yeah. If there is a need for a slide, you can always bring them up. Yeah, it's better to stop sharing, and then if you're able to, please turn your video on so that it enables more better communication and discussion from the team as well. Any questions, comments from the team? So when they looked at the surface, did they, in the supplementary information, did they have any surface analysis to see, say, for example, the EDAX, some EDAX, to understand the noble metal enrichment?
Okay, so this particular paper doesn't have this information, but it's kind of well known in the corrosion community that, you know, with these changes, we have differences in the surface film characteristics. But it was not critically discussed in this paper.
Understood, understood. Yeah. And the other question I had is, they talk about the pH, I think mostly on the bulk pH, right? The local pH, did they do any calculation on the volume element, doing something similar to finite element analysis to see what the local pH could be due to the changes that are happening?
Not really. They haven't done anything related to surface pH, but kind of a very quick understanding is that magnesium undergoes like enormous dissolution once we drop it in water. Mm-hmm. So I think that's why they assume that, you know, definitely it's going, there are going to be changes in the surface pH, but it's typical that they assume that with the changes in the bulk pH, they can find some differences, immediate differences in the results. So the answer to that question is no, they have not done any critical calculations for the paper.
Understood.
Yes.
Yes, go ahead.
I have one question on the experimental part.
Okay.
Regarding the scanning flow cell, I have gone through the paper during this talk, and they mentioned that they're changing the volume. The flow rate is very inch in microliters per minute.
Yeah.
In that case, the change in the surface, so due to flow velocity, whatever the passivation is formed, it may not remove. But in case if they're increasing the flow rate, will it going to affect the corrosion rate in the flow cycle?
Yeah. So I had an opportunity, so when I was in Monash, to look at this setup, you know, the electrochemical flow cell, it's kind of very delicate. One problem that we always end up in a flow cell is that, you know, electrolyte starts to, you know, clump, or it has a higher residence time, meaning it's not continuous, and sometimes they tend to get accumulated. So these flow rates always have to be optimized, so that we have a continuous flow of electrolyte and it just doesn't get accumulated in any part of the cell. So I think the flow cell, whatever they have done, is kind of optimized for that. But really, I don't think they have looked at that part of it, like what would happen. So how they achieve or how they decide that if this is optimum is by running a lot of calibration solutions into it, trying to calibrate it through the mass spectrometer, and then check if this is working. That's how they calibrate. So it's more towards that compared to how this flow rate is going to affect the dissolution kinetics.
Yeah, because I worried about the passivation film, which is going to come out because of flow. That is what I was wondering, how they have controlled that one.
No, can you please repeat it, because your voice is not very legible for me.
My question is, once the flow is happening, whatever the passivation film or whatever the new particle is formed on the surface, it will come out because of flow. So how they are tackling that point? Because we don't know if new surface exposed, there will be a higher corrosion.
The entire surface is exposed, right?
Yeah, I think if I paraphrase Ramesh's comment, it's what is the interaction of the flow in eroding the surface protective film and then leading to new corrosion versus the electrochemical dissolution of the protective film. So there is a corrosion and then the erosion. It's the mechanical interaction. There may be some interaction. I think I see this, Ramesh, as a science paper rather than an engineering paper.
Right.
So if it's engineering paper, yeah, definitely, I think it would have been a good idea to look at the, for example, as a function of Reynolds number, how does that impact, right? So you can look at that turbulence versus laminar flow and then look at it. So I see this as a science paper. From that point of view, they combined very well the techniques of understanding what's happening downstream by coupling the ICP mass spec. And yeah, go ahead.
Yeah, so just to add to that point, if you look at the last slide that I showed, which was done without the convection, electrolyte convection. So they kind of tried to compare the data without the electrolyte convection, which is the second setup that I showed, which had an inverted view rate and then a funnel to collect the volume of hydrogen. So they tried to compare this data with that data. However, as you see, the mass spectrometer in itself is very sensitive to small changes. So they had to change the chemistry a little bit. So I'm not sure to what extent they were able to really compare this data, but they were able to find a trend that was similar to the flow cell conditions. Yeah.
Got it.
Thank you.
Sridhar, you had a question?
Yeah, no, I also wanted to say the presentation was, first of all, it was very good. Like someone with no experience, like in corrosion, the beginning was helpful. And then this is kind of relates to the points that Ramesh and Chuck were just discussing. So once depending on whether it's erosion or electrochemically, when the film is gone somehow, when there's like a hole in that layer of film, how is it measured, like the new effect of like a new film forming?
Sorry, how does when there is a hole or a bare surface, then how does I didn't understand the last part.
So how did they measure or quantify the new film that is forming?
Okay, I think quantify and measure in the sense you're talking about the composition of the film.
So I think we're pretty. It'll just be magnesium hydroxide, right? For like this catalyst, but I guess because we have there's like a hole. Do we know that the film will still be like planar, or will that cause like any differences on like this interaction?
Yeah, so honestly, in this paper, they have not talked about the film characteristics very deeply, but the same group has been working on understanding that characteristics as well, and that's an entirely different study. So where they take the XPS and study what is the valency and everything like that. So so during such studies, they do find that there is a composition difference, but for this paper, they have not seen anything. They have not studied anything like that critically.
Okay, thank you.
Other questions or comments? Okay, if not, thank you very much, Gayathri. Really enjoyed the talk. Thank you for bringing a different topic and learned a lot today. Thank you. And we meet every week, Saturday morning Pacific time, Saturday evening IST, Saturday evening 8:30 p.m. and then Saturday morning 8 a.m. Pacific time right now. If you'd like to lead the discussion, please send us an email. Our email address is info@vetrylabs.com. Thank you so much. Looking forward to the next week's discussion. And that concludes our recorded session.